Question number 5, exercise 2.4. Prove the following properties. If z is real if and only if z equal to z bar. That is if then statement. If z is real, then z equal to z bar we should prove. Or if z equal to z bar, we can show that z is real. So now we take a complex number z as let z equal to x plus iy. Then its conjugate z bar equal to x minus iy. So now z equal to z bar implies if z equal to z bar, then it is a real number. Z equal to z bar given, which implies if and only if z equal to x plus iy, then which if and only if z bar equal to x minus iy. Z equal to z bar if and only if x plus iy equal to x minus iy. If and only if z equal to z bar, then we can simplify this as iy equal to minus iy. If and only if z equal to z bar, 2iy equal to 0. If and only if y equal to 0, which implies if and only if z equal to z bar, if and only if y equal to 0 means that is real, therefore z is real. And then the second property, similar to this way, prove that real part of z equal to z plus z bar by 2 and imaginary of z equal to z minus z bar by 2i. When I introducing conjugate of a complex number, we have derived those two results. They are the subdivision number 2 here. The second subdivision is, if we prove the properties, real part of z equal to z plus z bar by 2 and imaginary of z equal to z minus z bar by 2i. We have proved already, and now again improving the same result here. Let z equal to x plus iy, then z bar will be equal to x minus iy. Now here z plus z bar is needed. Add z and z bar, which is equal to iy and minus iy get cancelled. That is x plus iy plus x minus iy, which implies 2x z plus z bar. So z plus z bar divided by 2 will be equal to 2x by 2, that is x. In z, x is known as real part, y is known as imaginary part. So z plus z bar by 2 will be equal to real part of z here. And similar to that, z minus z bar equal to x plus iy. Minus of the z bar means minus x plus iy. Now cancelling these two real part, we have 2iy. So z minus z bar equal to iy. Z minus z bar by 2i will be equal to y. So y is known as imaginary part of z. So it is written as im of z, imaginary of z. That is z minus z bar by 2i. We have already proved when introducing the conjugate of complex number, the same result. Now it is in the subdivision number 2 of question number 5. Now question number 6. Question number 6. In the complex number root 3 plus I whole power n, find the least positive value of n. Find the least positive value when substituted in the power. The root 3 plus I turn as real number, and when it turn as purely imaginary. That is the question. We should find the value of n. When applying from least positive number to n, that will yield real number, and that will yield a purely imaginary number. So according to the power it will vary. So applying the power, we can conclude when it is real and when it is purely imaginary. So now root 3 plus I whole power n. Put n equal to 1. N equal to 1 means it implies root 3 plus I. It has both real and imaginary. Then n equal to 2. Because positive number, it should be least, means we should start from 1. So substituting n equal to 2 here, root 3 plus I whole power 2, expanding a square 3, b square means I square minus 1, plus 2ab means 2 root 3i, which implies 2 plus 2 root 3i. We can take 2 as common, 1 plus root 3i. that it also contains both real and imaginary part. Now put n equal to 3. N equal to 3 means root 3 plus I whole power 3. Already we have the value of root 3 plus I whole square. So write it here 1 plus root 3I into then one another root 3 plus I. Are you understand here? This is the value of root 3 plus I whole square. It can be splitted into root 3 plus I whole square into root 3 plus I. Now for root 3 plus I whole square I have written the above result, and then one another root 3 plus I remains. When multiplying these two, we will get the value of root 3 plus I whole cube. Now here these two are in a complex format. They are multiplied by using complex number 2 into, when we multiply real to real, 1 root 3, then root 3 1, then multiply here 1 into root 3, then multiplying the image, this is real part, this is imaginary, then multiplying imaginary part we should change sign, so root 3 into 1 minus root 3 plus I into, then corresponding multiplication of real to imaginary, imaginary to real, will have 1 plus 3, here we have 2 into 0 plus I4, which is equal to 8I. When the power n equal to 3, we are achieving this complex number as only purely imaginary complex number. When n equal to 3, therefore, when n equal to 3, root 3 plus I whole power n is purely imaginary. Purely imaginary. Now we are moving to the next one. First one is real. When it is real. Now we have checked 1, 2 and 3. Now for 4, n equal to 4, root 3 plus I whole power 4 equal to, whole to the power 4 equal to root 3 plus I whole square into root 3 plus I whole square. So we can multiply this result as twice. So 2 into 1 plus root 3I into 2 into 1 plus root 3I, which is equal to 2 2s are 4, and then here multiplying the same value 1 plus root 3I whole square by using a plus b whole square form. 1 b square means root 3I whole square, root 3 become 3, I square become minus 1, so minus, plus I into 2a become 2 into 1 2, 2 into root 3, so totally we have 2 root 3I here. So simplify it, 4 into minus 2 plus root 3I. So when we take the power 4, it is again again contains both real and imaginary part. When we substitute n equal to 5, and then we should multiply this by root 3 plus I. When we multiply again by root 3 plus I, we should have both a real part and the imaginary part in this case also. Now look at n equal to 3 value, 8I. Now n equal to 6, substituting n equal to 6 means root 3 plus I whole power 6. That will be equal to root 3 plus I whole power 3 power 2, which is equal to the value of root 3 plus whole cube is 8I power 2, which is equal to 64 into minus 1. 8 square 64, I square minus 1 equal to minus 64. Therefore, when n equal to 6, the complex number root 3 plus I whole power n, the complex number root 3 plus I whole power 6 is equal to minus 64 is real, purely real, or it is only real. So when n equal to 6, the root 3 plus I reach its it reach at a real number, only real number, and n equal to 3, it reaches only purely imaginary. Therefore, for n equal to 3, root 3 plus I whole power n is purely imaginary. And when n equal to 6, root 3 plus I whole power n is purely real. So the least positive integers are n equal to 3 and n equal to 6. When n equal to 3, it reaches purely imaginary. When n equal to 6, it reaches purely real. It can be completed in one another way by using polar form of a complex number. After completing when we introduce complex number, I'll teach again the question number 6 in different way. Now we are moving to question number 7. Show that 2 plus I root 3 power n 2 plus I root 3 whole power 10 and minus of 2 minus I root 3 whole power 10 is purely imaginary. That is first subdivision. And then for second subdivision we should prove 19 minus 7i divided by 9 plus I whole power 12 plus 20 minus 5i divided by 7 minus 6i whole power 12 is purely real. That is purely imaginary, the first one. Second one is purely real or real. To prove this is to show that first one is purely imaginary, second one is purely real. That is only real part contains. Now to prove the first one, we have a property: if z equal to minus z bar, then the given complex number z is purely imaginary. We have a property. By using this property we can easily derive this result. Now substitute the given complex number is 2 plus I root 3 power 10 minus 2 minus I root 3 power 10. Now applying the conjugate here, z bar equal to, this is taken as z, let z equal to 2 plus I root 3 power 10 and minus 2 minus I root 3 power 10. So now z bar equal to, taking conjugate, z bar equal to 2 plus I root 3 whole power 10 minus 2 minus I root 3 whole power 10 whole bar. Now z1 bar minus z2 bar, z1 minus whole bar equal to z1 minus z2 whole bar equal to z1 bar minus z2 bar. So by the way we can split this 2 plus I root 3 whole power 10 whole bar minus of 2 minus I root 3 whole power 10 whole bar. Now we have one another property, z power n whole bar equal to z bar whole power n. By using the second property, we can interchange this as 2 plus I root 3 whole bar power 10 minus of 2 minus I root 3 whole bar power 10. Now the conjugate of this one is 2 bar means nothing but conjugate, 2 minus I root 3 minus of 2 whole power 10, here 2 plus I root 3 whole power 10. After taking conjugate, it will be 2 minus I root 3, it will be 2 plus I root 3. Now we have minus, taking minus as common out, minus of, taking minus as common, this one turn as plus, this one as turn as minus. So 2 plus I root 3 whole power 10 minus of 2 minus I root 3 whole power 10, which implies 2 plus I root 3 minus 2 minus I root 3, that is a given complex number z. We have minus of the z, which yields a value of minus z. So we have started here z bar equal to minus z. Now we can interchange the sign here, minus z or minus z equal to z bar. This yields minus z equal to z bar. This yields the given complex number z is a purely imaginary. For the second case, we should show that this result is purely real, or it is real, it is a real number. So we should show that this given number is real. For that, I am taking the number inside a fraction 19 minus 7 by 9 plus I and multiplying by its conjugate 9 minus I by 9 minus I. This is a given number inside the bracket. Now take this one and multiply by its conjugate 9 minus I by 9 minus I. The denominator in the form of a plus ib into a minus ib. So that is a square plus b square, 9 plus 81 plus 1. Sorry, 81 plus 1. The numerator is 19 minus 7, real part, imaginary part. And then second complex number, real and imaginary are 9 minus 1. Multiply these two and change its sign. Now 19 9 of 1 of 19 9 here, 171 and then multiply these two plus 7 and change its sign minus 7 plus I into, just cross multiplying, minus 19 minus 63. Without sign you should multiply, cross multiply, you will get imaginary. Simplify that, we will get the answer as that is equal to here 164 and minus 70, 84, minus 84, 60, 70, minus 70, 82, sorry, 82, minus 82 divided by 82 into I. So 164 minus 82i by 82. We can separate this by dividing by 82, 2 minus I. This is the value of 19 minus 7i by 9 plus I. And the second one is 20 minus 5i divided by 7 minus 6i. Whole power 12 is given. Now simplify this in the similar manner. 20 minus 5i divided by 7 minus 6i into 7 plus 6i by 7 plus 6i, which will be equal to the denominator in the form of a minus b, a plus b, that is a square plus b square, 49 plus 6 square, 36. The numerator we have 20 minus 5 in the first complex number, real imaginary. The second one real 7, imaginary 6. When you multiply directly to 7 into 20, 140. And then here multiply and change its sign. 30, here is minus 30 means plus 30. And plus I into, just cross multiply without sign, 120 minus 35. Simplifying this, we will have 140 plus 30, 170 plus I into plus I into 85 divided by 40, then 70, 85. You can divide it again, dividing by 170 by 85, that is 2, here plus I, 2 plus I. Here we have 2 minus I, this one result is 2 plus I. Now substituting this 2 minus I and 2 plus I in the above problem, given problem, whole power 12, 19 minus 7 by 9 plus I will be equal to 2 minus I. So this is 2 minus I whole power 12, and plus this one is 2 plus I whole power 12. We have substituted the equal values of these two. Now this is known as the value of Z. Let it be Z. We have to prove this one is real. When Z is real, which implies Z equal to Z bar. So when we take conjugate to this one, it will yield the same value. So conjugate Z bar equal to 2 minus I whole power 12 plus 2 plus I whole power 12. Now by property we can separate the conjugate. 2 minus I whole power 12 whole bar plus 2 plus I whole power 12 whole bar. Now by the again one more property we have, by use of the property Z power n whole bar Z power n whole bar equal to Z bar whole power n. By the way, we can write this one as 2 minus I whole bar power 12 plus 2 plus I whole bar power 12. Now by taking conjugate, it will turn as 2 plus I whole power 12. Here 2 minus I whole power 12, which will be equal to Z. So the value Z bar equal to Z, which yields the value Z bar equal to Z, which implies, which is equal to Z, that is Z bar equal to Z. Here we can write Z bar equal to Z. We have started Z bar, we derived at Z. So Z bar equal to Z. This means the given complex number is real. Therefore, the complex number 19 minus 7i by 9 plus I whole power 12 plus 20 minus 5i by 7 minus 6i whole power 12 is real.